Namaste. Welcome to this channel Chemistry Made Easy by Dr. Ashok. Today we will discuss the remaining part, next part of the VSEPR theory, that is ligand close packing. That is ligand close packing. So this approach of ligand close packing was developed by Gillespie in 2000. In his approach, he considered the distance between non-bonded atoms, that is, the atoms which are bonded to the central atom and the which are further not bonded with each other. So the distance between non-bonded atoms is considered as the base for describing his approach. This distance between non-bonded atoms are consistent, and the bond distance, that is distance between central atom and outer atom, as well as bond angle, is changing within certain range. So this is his approach. What is the approach? The bond distance, means outer distance between outer atoms, are considered or taken into consideration, which are found to be consistent. But what is changing? Their change is taking place with bond distance and bond angles. So, which is shown here. For example, if we consider a series of molecules in which the central atom is same, but the outer atoms are different, then here you will find that if we consider such two series, that is BF2X and BF3X compounds, here the X is like F minus, OH minus, NH2 minus, hydrogen, NH, this PH3, that is like CF3, etc. So if we consider such groups present as the outer groups which are directly bonded to the central atom. So in such groups we will take these examples later on in the same lecture and we will discuss in detail. So in such molecules, that is BF2X with these variations and BF3X with these outer groups, the BF distance is ranging between 130.7 to 140.4 ppm. So the BF distance. So here you are finding that boron is bonding to F atoms. So the FBF distance is, that here BF bonds are 130.7 to 142.4, and the angle, this FBF angle, this FBF angle is 105.4 to 120. So there is some range which is valid, and the non-bonded atoms, that is FF, which are outer atoms, the distance is ranging between 225 to 229 ppm. Now we will see this in tabular form and explain in detail. So we will show here the molecules in tabular form. That is, we will see here examples. Then we will see here its a coordination number. Then BF distance in ppm. Then bond angle, FBF angle. Then FF distance. So we will see here some examples. For example, we will take the first molecule, that is BF3. So you will see that the structure of BF3 is like this. That is BF3, and its structure is F. So here you will find that the coordination number of this boron is 3. The BF distance, here it is 130.7. This distance is 130.7 ppm. Then the bond angle is perfectly 120 degrees. The FF distance is 226 ppm. So this distance, that is the FF distance, is this 226 ppm. Similarly, this FF distance is 226 in this BF3 molecule. Now we will take another example, that is BF2OH. That is BF2OH. So here in this structure, if we replace this fluorine by OH, this fluorine is replaced by OH, then the coordination number is also 3. The BF distance changes, it becomes 132.3. Then the bond angle becomes 118 degrees, and this distance becomes 227 ppm. Now in third molecule, if we replace this OH by NH2, BF2 NH2, the coordination number is same. This BF distance changes, it becomes 132.5. The angle becomes 117.9 degrees, and this becomes FF distance 227 ppm. Again, we will see one more example, and then we will see the details. Again, if we consider another molecule, that is BF2Cl, the coordination number remains same. The BF distance is 131.5. The bond angle is 118.1 degrees, and this distance is 226. So these are found to be the examples of this type of pattern, that is BF2X. So here in this example, we will see that the BF2, now if we see this BF2 here, it is OH. Then you will find that the molecule OH is strongly, the oxygen is strongly electronegative compared to this boron. So what will do? It will attract the electrons here towards it. So the electrons are moving away, as well as size of this OH is large. So because of this, these F atoms are pushed away. As a result of this here the bond angle is reduced. This FF bond angle. This FF bond angle is FF bond angle is reduced to 118 degrees, whereas the distance BF distance here it becomes 132.3. This BF distance becomes 132.3 ppm. So compared to this BF3, as we say the ideal molecule example, in the BF3 it was 130.7, but here it becomes 132.3. So there is slight increase in the BF distance. Why it is so? This is because of the this lone pairs on this oxygen as well as the shape. These bond pairs are pushed away, so the bond angle is reduced. And the FF distance is also, you will find here, the FF distance is also increasing. So these FF are moving away. So this is within some range, slight difference. So this is in case of this BF2H. Now if we see the BF2NH2, the coordination number is same. We will take here NH2. So here the BF distance is 132.5. It is slightly more. It is slightly more. And the bond angle is nearly the same, 117.9. So there is no more change. Slight change, 107.9 degrees. And the FF distance is also same. So this effect of the slight change in BF distance and slight change in bond angle is because of this NH2, that is outer atom or group, that is we say that is ligand. So these are having their effect of size and electronegativity. The lone pairs on this nitrogen are also having effect on this bond distance as well as BF angle. Now in this case BF2Cl, you will find that if we take Cl, here the distance is 131.5. This angle again increases, it becomes 118.1 degrees. So there is increase in the size, increase in the bond angle. So this is because of the electronegative properties and lone pairs of electron. That is because of the ligand close packing. So this is showing effect on these bond pairs of fluorines, and this one is slight change. So this is the example of say BF2 type of compounds. So that is BF2X type. Now we will see the examples of another type. That is BF3 X. So here we will see the first example, that is BF4 minus. So the structure of this BF4 minus is like this. So this is tetrahedral structure. The structure of BF3, it was planar, triangular, having characteristic bond angle, that is 120. But here in this case the bond angle is the bond angle is 109.5 degrees. So if we see the coordination number here, it is 4. The BF distance, you will find it is 138.2. Then the bond angle FBF is 109.5. That is perfect tetrahedral distance, and this FF distance is 226. So here all fluorines, all are same atoms. So the bond angle is same everywhere. The distance, BF distance is 138 point. Now we will see another example in which we are replacing the X, that is changing the X. So we will take another example of BF3 CH3 minus. So here coordination number is same. So if we replace any one, say if we replace this by CH3, then it will have effect on these remaining fluorines. So the BF distance is changing to 142.4 ppm, and the angle becomes 105.4 degrees. The effect distance becomes 227. So because of changing this F, 1F or X is taken as CH3, then it shows effect on this BF bond. The BF bond is changed, it is increased because of this CH3. So here CH3 has some electron donating effect, that is it supplies electron to this molecule. As a result of this, the bond angles are reduced and the FF distance is slightly increasing, Again, if we take other example, that is BF3 CF3, coordination number is same. The BF distance is 139.1. The bond angle is 109.9, and the FF distance 228. So here you could replace this CH3, so that is we will show here as X. So when X is this CF3, so CF3 has effect on the bond distance. So this bond distance is less than that is by CH3. Why it is so? Because the CF3 carbon is here, carbon is attached to fluorines, and fluorines are electron withdrawing. So carbon will also further withdraw electron cloud from boron. So this will have certain effect. Further, the CF3 is also bulkier group than CH3. So it will occupy more space. As a result of this, the FF distance, this is the bond angle, is also changed. So the bond angle becomes 109.9 degrees, and FF distance also slightly changes. Then we will see last example, that is BF3, pH. Coordination number is same. The BF distance is 137.2. The bond angle is 112.1 and this distance 228. So there is also effect of this pH3. If we take here pH3, you will find a change in the BF distance. It decreases, the bond angle increases. So this is the effect of the pH3. So pH3 is also a larger molecule, so it will also repel the neighboring fluorines, and as a result of this they will occupy still larger distance. So the distance will be compared to this. The BF distance is short here, slightly reduced, but the bond angle is increased. Bond angle is increased. So these are the various effects observed on the molecule. So this is explained by the Gillespie in 2000. So we will stop here. Thank you very much. Please press the bell icon and like button and subscribe to this channel. Share this channel to your friends. Thank you very much.